countdown.
Congratulations! This live broadcast is specially brought to you by Academy YouTuber Malaysia, an initiative by eDidik Malaysia and Kelab Guru Malaysia. Please pay attention. The live broadcast will begin shortly. The link to the certificate of attendance will be provided at the end of the session. Please make sure it is filled within the stipulated time. Thank you.
Hi! Good evening, teachers, parents, and all wonderful students. Welcome to Pusat Tuisyen Academy YouTuber. Permula percuma, selamanya percuma. How are you doing today? I hope all of you are ready for today's lesson. Before we proceed, let's begin our section by reciting a prayer for Muslim. The non-Muslim may pray according to your religion. Okay, let me introduce myself. I'm Teacher Kong from College Matrikulasi Perak, the moderator of the day. We at Pusat Tuisyen Academy YouTuber will provide you with free online classes. Let's take this opportunity to do your revision. So, are you ready? Okay, let me introduce our teacher for today's lesson. We have Teacher Tang from College Matrikulasi Selangor. We are now live on Teacher Tang channel. Please support her channel by clicking subscribe now. The topic of today's lesson is physical properties of transition matter. And together with us, we also have Cikgu Shanul from College Matrikulasi Pulau Pinang, who is control host, in charge ensure the smoothness of our lesson on technical support. And Teacher Vivi Lau from Pusat Tingkatan 6 SMK Tinggi Klang as observer to ensure the smoothness of our lesson. So before we begin, I have a few reminders to all of you. First, please pay attention to our lesson, stop chatting, and use the chat section wisely. Number 2, regarding certificate link, the link will be given at the end of our section. Please use eDidik account when you fill in your particular and make sure to listen to the passcode given from time to time. Okay, so now I would like to announce the first passcode. Okay, please pay attention. The first passcode is A0. 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 Okay, so without further ado, let's welcome Teacher Tang.
Okay, so I'm Teacher Tan from College Matrikulasi Selangor. I have 8 years of experience teaching chemistry. So this is my teammate for chemistry pre-U. So we all led by Cikgu Shannon. So in the group, we have Teacher Vivi Lau, me, Cikgu Mawar, and also Teacher Kong. And for the mathematics pre-U group, we have the leader is Teacher E. So we have Teacher Eileen, Teacher Zana, and others. So and for the pre-U biology team, so led by Cikgu Faiza. And then for physics pre-U, led by Cikgu Rosmaya. And this is the pre-U group for accounts and economy. So now we move on to look at our topics for today. So today I will go through transitions elements, particularly on the physical properties of first row transitions elements. So before we look at transitions elements, we shall look at D block elements and their electronic configurations. So why do we need to look at their electronic configuration? It is because the electronic configuration is closely related with the properties of the transitions elements. Because of that, we need to look at the electronic configurations closely so that we can deduce their properties. Okay, so D block elements, so basically D block elements refer to elements in group 3 until group 12. So from the electronic configuration, we can see that for the D block elements, their general valence electronic configuration So basically is sorry about that.
It's okay. Let's continue. Okay, student, please pay attention. Okay.
Okay.
Okay, teacher Tang will share again soon.
Okay.
So you maybe now all of you can try to take out your periodic table and check where is the transition matter, okay, located at which part of the periodic table. Okay, is it group F, group P, group S, or group D? Okay, block. Oh, sorry, it's block. Block F, block S, block P, and or block D. Here, please take out your periodic table and check. Okay, yeah, let's start again.
Okay. Okay, sorry about that. Okay, so the D block elements, if we look at their electronic configuration, we can see that for the D block elements, they're all having the valence electronic configurations of okay, it's okay. So we can see that their general valence electronic configuration is 3dx 4s2. So this is their general electronic configuration. Okay, so what does it mean? It means that for the D block elements, so they all, so it's according to the APA principle, need to fully fill the lower energy 4s orbital first, and then only occupy the higher energy. The remaining electrons will go to the higher energy 3D subshell. Okay. So this is the general valence electronic configurations for the D blocks elements. However, from the valence electronic configuration, we can also identify that there are two elements in the D blocks, okay, first row of the D blocks, that is not according to the pattern 3dx 4s2. So the first element is chromium. So chromium, so supposedly according to APA principle, the valence electronic configuration should be argon 3d4 4s2. Okay, so this is according to the APA principle. However, the actual electronic configurations of chromium is actually argon 3d5 4s1. So why? So it is basically by looking at the actual electronic configurations of chromium, we can see that one of the electrons from the 4s subshell, okay, is being moved into the 3d subshell in order to give 3d5. And this 3d5 basically is half-filled 3d subshell. And this half-filled 3d subshell basically give chromium extra stability. So because of this extra stability, chromium has the unusual electronic configurations of argon 3d5 4s1 instead of argon 3d4 4s2. So beside chromium, so copper is another element, first row of D block elements, which has unusual electronic configuration. So for copper, so APA principle, we will predict that copper should have the electronic configurations of argon 3d9 4s2. However, the actual electronic configurations of copper is actually argon 3d10 4s1. Again, one electron from the 4s subshell move to the 3d subshell in order to give us 3d10. So this 3d10 is completely filled 3d subshell. And just like the half-filled 3d subshell, this completely filled 3D subshell is also more stable. So because of that, these two elements, first row of D block elements having the unusual electronic configuration. Okay, and this half-filled 3D subshell and completely 3D subshell with extra stability, also something we need to take note, and I will later on explain about this more in the ionization energy, where we can see that some ions having this extra stability to cause them to have certain oxidation state. Okay, so then now we move on to look at what is definitions of transitions element. So transitions element, basically it is referring to, and it is strictly defined as, an element that forms at least a stable simple ion with incomplete or partially filled d orbitals. Okay, so transitions element refer to the element with at least forming a stable simple ion with incomplete or partially filled d orbitals. So because of this definition, therefore scandium and also zinc are not transitions element. Why? Because scandium only can form scandium 3 plus ion. When it forms scandium 3 plus ion, the 3D subshell will be empty. So this is not fulfilling the definitions of transitions element. Therefore, scandium is not a transitions element. So besides scandium, zinc is also another element that do not fulfill the definitions of transitions element. So zinc only forms zinc 2 plus ion. And zinc, when forming zinc 2 plus ion, we can see that the 3D subshell is fully filled, completely filled with electrons. But then the definition, it must be incomplete or partially filled. So because of that, zinc is also not a transitions element according to the definitions of the transitions element. So because of that, so the first row of transitions element, because of this definition, therefore the first row of transitions element only consists of 8 elements, which is from titanium to copper. Because these 8 elements fulfill the definitions of transitions element strictly. So, and we must know that for transitions element, okay, when they want to form ions, so when the transitions metal atom forming ions, the electron will first remove from the 4s subshell first. Then only remove from the 3D subshell. So why? It is because 4s and also 3D subshell, they are very close in energy. When the 3D subshell is empty, so the 4s subshell is lying at lower energy level. That's why, according to Akbar principle, need to fill the lower energy 4s subshell first, then only fill the higher energy 3D subshell. But once electron occupying the 3D subshell, it will actually repel or push the 4s electron to higher energy level. So when the 4s electrons are at higher energy level, so when forming ions, electron need to remove from the higher energy 4s subshell first, then only can remove the electron from the 3D subshell. So I give you example. So iron atom. So iron atom, if we look at the periodic table, so the proton number is 26, so means that iron atom consists of 26 electrons. So according to Akbar principle, need to fill in the lower energy orbital first. So 1s first, followed by 2s, followed by 2p, followed by 3s, followed by 3p, then 4s. So up to 4s already fill in 20 electrons. So means that another 6 electrons need to fill into the higher energy 3D subshell. So, but once the 3D subshell is filled with electron, what will happen is this electron filling the 3D subshell, so will repel. Will repel this 4s electron to higher energy level. So before this, it is at lower energy level. Now it is because the 3D subshell is being filled with electron, so the 4s subshell electron will be pushed to higher energy level. Okay, so up to here already filled in 21 electron, but iron atom 26 electron. So the rest will go into the 3D subshell. So this is the electronic configuration for iron atom. So I simplified it. So it's argon. So 4s2 will be filled first, and then 3d6. But once the electron fill in the 3D subshell, it will push the electron in the 4s to higher energy level. Okay, so means that when want to form the ion, so since that now the 4s subshell is at higher energy level, so when want to form the Fe3 plus ion, we need to remove 3 electrons. So the electron will start to be removed from the 4s subshell first, then only the 3D subshell, because the 4s subshell electrons is at higher energy level to give us the Fe3 plus ion having the electronic configuration of argon 3d5. Okay? So now question number 1. Which of the following is the most accurate definitions of transitions element? So this is very easy. So any answer from students?
For the time being, no. We wait for a while and see.
No. Okay. So just now I mentioned already, for transitions element, it has a very strict definition. It has a very strict definition. Remember, when forming the ion,
there is one answer from Edison. Yeah.
Okay. So what is his answer?
His answer is B.
Okay, very good. The answer is B. Must remember, for transitions element, the definition is very strict. Okay, when forming ion, at least one of the ion, okay, so we partially fill d orbitals. Okay, partially fill d orbitals. So that's why the answer is B. And because of this, scandium and zinc are not being considered as transitions elements. So we move on. So to look at the first physical property of transitions element, the atomic radii. So for transitions element, first law of transitions element, so just now I told you already, is from titanium to copper. It's from titanium to copper. So if we look at their atomic radii, so and compare it with the S block element, so we can see that the first row transitions element, the atomic radii is actually smaller compared to the S block elements of same period. Okay. However, in between them, there is only little variation, only little change in the atomic radii. Why? Okay. So we know that as across the transitions, first row transitions element from titanium to copper, the proton number increases. The proton number increases. So when proton number increases, means that the nuclear charge increase. Okay, but then at the same time, the number of electrons in the inner shell also increases by 1. Okay, also increases by 1. Okay, so because of that, so proton number causes nuclear charge to increase. And then proton number causes nuclear charge to increase. So nucleus attraction supposedly should be stronger. But then also first row of transitions element also have one electron being added into inner 3D subshell. Okay, and this causes the screening effect to increase as well. Okay, so nuclear charge causes attractions to increase, but screening effect causes repulsions to increase. So because of that, so increase in the nuclear charge basically is already been cancelled out by the increase in the screening effect. So because of that, across the first row of transitions element, there is only a little change in the atomic radii, because the nuclear charge, increase in nuclear charge is cancelled out by the increase in the screening effect due to one extra electron is being added into the inner 3D subshell. Okay, so must remember this. But then, if we plot it into graph, we can see that manganese having unexpectedly larger ionic radii. So why? So we can see this from the electronic configurations of manganese atom. So manganese atom having half-filled 3D orbitals, okay, and also fully filled 4s orbital. And because of these half-filled 3D orbitals, it will give larger or greater repulsion on the outermost shell 4s orbitals. So because of that, so manganese has larger atomic radius than expected. So again, it is because of the half-filled 3D subshell of the manganese orbital causes greater repulsion on the 4s orbital. So when repulsion is greater, then it will cause the attractions to be weaker. So the manganese atom to have larger size or larger atomic radius than expected. So beside manganese, so we can also see the outward trend for copper and also zinc. So why? So similar explanations as well. So for copper, we can see that the 3D subshell is fully filled or completely filled, and so as zinc, it is fully filled or completely filled 3D subshell. And this fully filled 3D subshell will give greater electron repulsion, greater screening effect on the 4s subshell electrons. And when the screening effect is greater, so means that now the 4s electrons are being shielded further from the nucleus. So because of that, copper and zinc will have larger atomic radii as well. So after, we have seen the atomic radii. Now we move on to look at ionic radii. So for positive ions, always have smaller ionic radii than their respective atoms. For example, iron atom and also ion, 3+ ion. We will expect ionic radius than iron atom. So why? We can straight away tell the answer by looking at the electronic configuration. From the iron 3+ ion, we can see that it has less electron. So when have less electron, means that the electron-electron repulsion is less in the ion compared to in the atom. That's why positive ions always have smaller ionic radii than their atoms. And for ions of given charge, the radius decreases slightly with increase in proton number. So what does this mean? So for example, for a given charge, ions of given charge, for example, titanium 2+ ion. So titanium 2+ ion, and also iron 2 plus ion. So we will expect iron 2 plus ion with larger proton number to have smaller size or smaller ionic radius compared to titanium 2 plus ion. Okay, so again, because larger proton number, so larger proton number means that greater nuclear charge, so greater effective nuclear charge, so will pull the remaining electrons stronger, so we'll expect to have slightly decrease in ionic radius. Okay, so ionic radius decreases with increasing oxidation states. So what does this mean? So for example, if we have Fe2 plus ion and also Fe3 plus ion, so Fe2 plus ion, okay, let me write the electronic configuration first. So we can see that Fe3 plus ion has less electron. So less electron repulsion. So definitely the ionic radius will be smaller because the attractions of the nucleus on the remaining electrons is stronger. Less electron, so less electron repulsion. So smaller size. Okay. So now we move on to look at densities. So how about the densities? So if we compare the first row transitions element density with the S block element, we can see that the density of the first row transitions element is larger compared to the respective S block elements. So why are they having larger density? So we know that density is equal to mass over volume. So just now already mentioned, the first row transitions element has smaller atomic radii. So when have smaller atomic radii means that they will have smaller volume. So in general, so the transitions metal atoms, they are more closely packed in the crystal lattice. So that's why they have smaller volume. So when smaller volume means that they will have larger density compared to the S block elements of same period. However, when across the first row transitions element from titanium to copper, the density increases gradually. We can see that the density increases gradually. So why? Okay, so it is because, so when across the first row of transitions element, the atomic mass increases. We know that atomic mass is due to number of protons and neutrons in the nucleus. So as the atomic mass increases as across the first row of transitions element, so the masses increases. So this causes the atomic mass increases. So this causes the slight decrease. With the slight decrease in atomic radii, so causes the density of the elements to increase gradually. So then we move on to look at melting and boiling points. Melting and boiling points. So for the first row of transitions element,
Hi, Teacher Tang.
Yes.
All right. Okay, let's have advertisement first. Okay.
Oh, okay.
Berita baik untuk semua. Kini, Akademi YouTuber memperkenalkan sistem mata gancaran kredit AYU untuk dikumpul. Jom ikuti kelas tuition live AYU untuk mengumpul kredit AYU dan berpeluang menebus hadiah-hadiah yang menarik. Hadiah bernilai lebih RM10,000 disediakan secara percuma untuk pelajar seluruh Malaysia. Apa tunggu lagi? Tebus ganjaran hebat ini sekarang. Layari www.academyyoutuber.com untuk maklumat lanjut.
Okay, welcome back. Before we continue our lesson, I will announce the next passcode, which is 9. 9. 9. Okay, now let's continue with Teacher's Tang lesson.
Okay, thank you. So now we move on to look at melting and boiling point. So for transitions, first row of transitions element, so they have relatively higher melting points and boiling points compared to the S block elements. Okay, so their melting point generally is above 1000 degrees Celsius and boiling point above 2000 degrees Celsius. So why? Okay, so we know that S block element, the S block matter, the S block elements and also first row of transitions elements, they are matters. So melting point and boiling points will tell us how strong is the metallic bond in the matters. Okay, and we know that the strength of metallic bond basically depends on the number of electron contributed by an atom to form the sea of delocalized electrons or metallic bond, and also depends on the atomic radii. First row of transitions element have a higher melting and boiling point. It is because their metallic bond in the solid lattice is stronger. So why the metallic bond is stronger? It is because the 3D subshell and 4S subshell, they are very close in energy. So when they are very close in energy, so means that the transitions matter, they can use both the 3D and the 4S subshells electron for metallic bond formation. So they can use both 3D and the 4S subshells electron for the metallic bond. So because of that, the metallic bond is stronger. That's why the first row transitions element has higher melting and boiling points. And then if we look at the graph, we can see that the manganese and also zinc, they have relatively lower melting point and boiling points. Why? So again, to know why they have relatively lower melting or boiling point, we need to look at the electronic configuration. So for manganese, can you see that it is 3D5, and this 3D5 is half filled. And remember, half filled have extra stability. So because of this 3D5 half filled stability in manganese causes manganese not to be able to use the 3D electrons for metallic bond formation. So since can't use the 3D half-filled electrons for metallic bond formation, therefore the metallic bond in manganese is weaker. That's why it has lower melting and boiling points. So as for zinc, so we can see that it is 3D10 here. So 3D10 is completely filled 3D subshell. So again, having extra stability, so means that these 3D10 subshell electrons are not available to form metallic bond. So the metallic bond in zinc is therefore weaker, causes zinc to have lower melting and boiling points. So question number 2. So why first row transitions elements have higher melting points above 1000 degrees Celsius than S block elements, than S block matter? So any answer from the students?
Okay.
So again, melting
but
point.
let's wait for a while.
Okay. So again, melting point indicate the strength of the metallic bond. So first row of transitions element have higher melting point, so means that the metallic bond is stronger. So what causes the metallic bond to be stronger? Any answer from the students?
Edison Yap answer C.
Oh, very good. The answer is C. So again, first row transitions element. So why can have stronger metallic bond? It is because the 3D and 4s subshell closer in energy. So the transitions element matter can use both 3D and 4s subshells electrons to form metallic bonds. That's why have stronger metallic bond, higher melting points. Very good. So now we move on to look at electrical conductivity. So electrical conductivity depends on how many electrons forming the sea of delocalized electron. So for transitions, first row of transitions element, so remember the 3D and 4s subshell, they are very close in energy. Therefore, the first row transitions element can use both the 3D and 4s subshells electron to form the sea of delocalized electron. So since many electrons, the 3D and the 4s subshells electron forming the sea of delocalized electrons, therefore they generally have relatively higher electrical conductivity. Okay, so now we move on to look at ionization energy. So if we look at the main group, the S block and P block elements, the first ionization energy of the element increases, okay, as across the period due to increase in effective nuclear charge. As we know that across the period, proton number increases, causes effective nuclear charge to increase. So the atomic radii become smaller. So that's why for the main group element, as across the period, the first ionization energy increase. Then how about first row of transitions elements? So for first row of transitions element, there's only a little variations in the first ionization energy. So means that their first ionization energy from titanium to copper not change much, only little variations. Why? So the reason is similar with the atomic radii. Remember, the atomic radii only change a bit. Why only change a bit? It is because so the 4s outer shell electron are being shielded from the nucleus attraction as the screening effect increases when the electrons are added into the 3D inner subshell. So remember, across the period from titanium to copper, so proton number increases, causes the nuclear charge to increase. But at the same time, one electron is being added into the 3D inner subshell. Okay, so 3D inner shell. So proton number increase in nuclear charge attraction, So because due to increase in nuclear charge, but then this is cancelled out by increase in the screening effect, as one extra electron is being added into the inner 3D subshell. So since it is being cancelled out, that's why the atomic radii stay almost the same. So same reason goes for the transitions, go for the first ionization energy, okay? Because the screening effect cancel out the increase in the nuclear charge, causes the first row transitions element to have only little change in the first ionization energy. So generally, the first and second ionization energy for the first row of transitions elements only change a bit. Okay, so why only change a bit? It is because the first two electrons are being removed from the outer 4s subshell. So, and this 4s subshell is well shielded from the nuclear attraction due to the increase in screening effect when one extra electron is being added into the 3D subshell. Okay, so again, the first two electron is being removed from the 4s subshell, and this 4s subshell is shielded from the nucleus attraction, okay, because of the one extra electron being added into the inner 3D subshell. However, if we look at the second ionization energy, the second ionization energy is higher than the first ionization energy. So second ionization energy is always higher than the first ionization energy. Why? So we know that when one electron is being removed, then the remaining electron will be attracted stronger by the nucleus. So when being attracted stronger by the nucleus means that if you want to remove the next electron, the second electron, more energy you need to put in to remove the second electron. Because of that, the second ionization energy always will be higher than the first ionization energy, because harder to remove an electron from a more positively charged ion. And we can see that for chromium and copper, both of them have larger second ionization energy than expected. Okay, so why? So we know that, so shall we look at chromium first? So for chromium, first electron removed from the 4s subshell. Second ionization energy is the energy that is used to remove the second electron. Can you see that? The second electron need to be removed from the half-filled 3D subshell. And we know that this half-filled 3D subshell is more stable. Because of that, chromium has an unexpected higher second ionization energy. So as copper. So first electron is removed from the 4s. Second ionization energy is to remove the second electron. And can you see that second electron is being removed from the 3D subshell, and this 3D subshell is completely filled 3D subshell. And this completely filled 3D subshell again having extra stability. So because of that, more energy need to put in to remove the second electron from copper. And because of that, copper also have unexpectedly higher second ionization energy. So now we move on to look at manganese have higher third ionization energy. So manganese has higher third ionization energy. Why? So again, so first two electron is removed from the 4s subshell. So third ionization energy is removing third electron. Can you see that the third electron need to remove from the half-filled 3D subshell? And this half-filled 3D subshell is more stable. Therefore, more energy need to put in to remove the third electron of manganese. That's why manganese has higher third ionization energy. So for iron, it has higher fourth ionization energy. So why? So again, first two electrons removed from the 4s subshell, and the third electron need to be removed from the partially filled 3D subshell. So let me write here. So after remove 3 electron, after remove 3 electrons, so this is the electronic configuration. So this is the electronic configuration. So can you see that now if we want to remove another electron from Fe3 plus ion, we need to remove it from the half-wheel 3D subshell. And this half-wheel 3D subshell is more stable. Therefore, we need to put in more energy to remove the 4th electron of iron. Therefore, iron has higher 4th ionization energy. So if compare with the main block element, we can see that for first row transitions element, the successive ionization energy increase gradually. So if main block, previously I already had a lesson with you all. So if main block element, we can use the successive ionization energy to find the largest difference. The largest difference then indicating that the next electron is removing from the inner shell. But then for the first row transitions element, their successive ionization energy will only increase gradually. So means that you cannot find the largest difference among them. Okay, so why? It is because for the first row transitions element, why the successive ionization energy increase gradually? It is because the 4s and 3d electrons, they are very close in energy. So since they are very close in energy, so the successive ionization energy will only increase gradually. So you can't find the largest difference between any of the successive ionization energies. So now the third question, why iron has lower third ionization energy? So why iron has lower third ionization energy? Any answer from the students here?
Not yet. Maybe Teacher Tang can give some clue to students.
Okay, sure. So first 2 electrons are being removed from the 4s subshell. The third electron need to be removed from the 3d subshell. The third electron need to be removed from the 3d subshell. So
okay,
let me quickly. Yeah.
One of the students.
Any answer from the student?
C.
Okay, the answer is D. Okay, so C is if it is 4th ionization energy, then to remove 4th electron, then it will be C. But now it's 3rd ionization energy. Why is it lower? So shall we have a look? So the 3rd electron is being removed from the 3d subshell. So which is the 3rd electron? This is the 3rd electron. So this is the 3rd electron. And can you see that this 3rd electron is being removed from one of the orbitals of 3D. And this electron are pairing out. When pair out, they will have mutual repulsion. So because of this mutual repulsion, therefore, it is very easy to remove the 3rd electron from Fe2 plus ion to form Fe3 plus ion. Okay, so again, due to the electron pairing out in one of the 3D subshell, so causes increase in the mutual electronic repulsion. So because of that, less energy needed to remove the 3rd electron to cause iron to have lower 3rd ionization energy. Okay. So, but if 4th ionization energy, it will be higher because 4th electron is removed from more stable half-wheel 3D subshell. But 3rd electron, mutual electronic repulsion in one of the 3D orbitals, so causes less energy needed to remove the 3rd electron. So we move on to look at the fourth question. So why iron has higher fourth ionization energy? So I already told you the answer actually. So why fourth electron why iron has higher fourth ionization energy? So any answer from students?
Let's wait for a while. Just now,
Okay.
Edison answer question 3 correctly. He answered D for the question 3, answer correctly. Now let's wait for him to answer question 4.
Oh.
Okay, now there are 2 students answer. Question 4 is C. Justine answer for C. And then Edison, your answer C as well.
Yeah, the answer is C. So I told you already, it is because okay, let me quickly write. So the fourth electron, so we want to form Fe4+. So the fourth electron is removed from the half-filled 3D subshell. That's why higher fourth ionization energy, because you need to put in a lot of energy to remove electron from the more stable 3D half-filled 3D subshell. Okay, so to summarize the general properties of first row transitions element. So basically, first row of transitions element, their atomic radii, okay, small compared to the main group. They are small and do not change much across the period. Okay, because increase in nuclear charge is balanced out or cancelled by the increase in screening effect as extra 1 electron is being added into inner 3D subshell. Okay, and for the density is higher compared to the main block elements and increase gradually across the period because the molar mass increase or atomic mass increase, okay, with the slightly decrease in atomic radii. Okay, melting point, boiling point, and electrical conductivity are high because melting point, boiling point high because stronger metallic bond. So due to close in energy between 3D and 4s subshells, so can use 3D and 4s subshells electron to form metallic bond. So, and also because 3D and 4s subshell very close in energy, so can use 3D and 4s subshells electron to form C of delocalized electron. That's why higher electrical conductivity. And their ionization energy increase gradually across the period. So now we move on to look at the last learning outcome, comparison between physical properties of transitions elements with calcium. So for this, I use titanium as the comparison with calcium. Okay, so for calcium, from the electronic configuration, we can see that both calcium and titanium, they have 4 shells filled with electrons because their highest principal quantum number are 4. So means that both of them have 4 shells filled with electron and both of them have 2 electrons in the outermost shell. Okay, and then previously we have seen from titanium to copper, across the first row transitions element, proton number increase. Okay, but then the number of inner shell electrons also increase as well. So the increase in nuclear charge is cancelled out by the increase in screening effect. Because of that, the first row of transitions element, they do not have much change in effective nuclear charge, and therefore their atomic size remain almost constant. But how about between the calcium and titanium? Can you see that if we compare between calcium and titanium, calcium is the main block element compare it with titanium, the transitions element, first row transitions element, can you see that calcium has much larger atomic radius compared to titanium? Why? So atomic size, okay, so calcium larger, titanium smaller. Okay, so why? So it is because proton number increases. So titanium has larger proton number, okay, compared to calcium. And then for titanium, the extra electron are being added into 3D subshell. And this 3D subshell, okay, so if compared to MEM block, 3D subshell, their screening effect is less effective. Okay, so less effective. Okay, so the screening effect is less effective compared to S and P electrons. So because of that, the increase in nuclear charge in titanium is still much more significant compared to increase in screening effect. Okay, so this also causes the effective nuclear charge of titanium to be larger, and the attractions of the electron of nucleus on the electron cloud in titanium to be larger compared to in the calcium. Because of that, the titanium will have smaller size. So again, so for titanium, calcium and titanium, so proton number of titanium larger. And then for titanium, the extra electron is being added into 3D subshell. And this 3D subshell cannot shield or screen the 4s subshell electron very effectively. Okay, so cannot repel 4s electron effectively. So because of that, the effective nuclear charge of titanium is still much higher compared to calcium. So since the effective nuclear charge of titanium is still much higher, so the attraction of the nucleus in the titanium atom on the electron cloud is still much stronger, causes titanium to have smaller size compared to calcium atom. So if compare the ionic radius, we can also see that even though both of them having calcium 2+ ion and titanium 2+ ion, having 3 shells filled with electron. So having three shells filled with electron. So again, the extra electron in the titanium is going into the 3D subshell. And this 3D subshell cannot shield effectively. Okay, but titanium ion still have larger proton number. So means that the effective nuclear charge in titanium ion is still larger compared to in the calcium ion. So because of that, titanium 2+ ion still have smaller size than the calcium ion. So again, proton number of titanium ion larger, so nuclear charge of titanium ion larger. And the extra electron is in the 3D subshell, can't shield effectively. So when can't shield effectively, means that titanium 2+ ion has a larger effective nuclear charge compared to calcium ion. So larger effective nuclear charge means that the nucleus of the titanium 2+ ion will attract the remaining electrons stronger. Therefore, titanium 2+ ion will have smaller ionic size than the calcium 2+ ion. So how about the density? So again, density is equal to the mass over volume. We know that for transitions element, first row transitions element, they have smaller atomic radius. So smaller atomic radius, so means that their volume will be smaller. Again, their volume will be smaller. From calcium, we compare calcium and titanium. So can you see that titanium also has larger molar mass, so larger atomic mass? So both these factors causes titanium to have larger density compared to calcium. because it has smaller atomic size and also larger molar mass. So causes titanium atom to have larger density than calcium atom. Okay, so we move on to look at the melting point. So the titanium and calcium, both of them, they are metal, so having metallic structure. So for titanium, so titanium is the first law transitions element. So can you see that the 3D and the 4s subshell electrons are available to form the metallic bond. But for calcium, only the 4s subshells electrons are available to form the metallic bond. So since more electrons to form the metallic bond, so the metallic bond in titanium will be stronger. So we will expect the melting point of titanium to be higher than calcium. So for electrical conductivity is also the same. So titanium, so can use the 3D and 4s subshells electron to form C of delocalized electron. For calcium, only 4s subshells electron forming the C of delocalized electron. So titanium can contribute more electron to form the C of delocalized electron. Therefore, is a better electrical conductor compared to calcium. For the first ionization energy, so just now I already mentioned titanium. So proton number larger, extra electron is being added into the 3D subshell, can't shield the 4s subshells electrons effectively. Because of that, the effective nuclear charge of titanium is higher. So when the effective nuclear charge is higher, means that in titanium, the nucleus can attract the electron cloud stronger. So when it can attract the electron cloud stronger, means that more energy is needed to remove the first electron from the 4s subshell. Okay, therefore titanium has larger or higher first ionization energy than calcium. So last question number 5. So calcium and nickel, both of them have 2 electrons in the outermost shells. So why nickel has higher electrical conductivity than calcium? So very easy. Oh, time's up. So any answer from the students? So why nickel has higher electrical conductivity?
For the time being, not yet.
Okay. So calcium main explore element, nickel is the first law transitions element. So why nickel has higher electrical conductivity than calcium? Any answer from students? Okay.
Okay, there is one answer from Edison Yap, C.
Okay, very good, very good. The answer is correct. So first law of transitions element, 3D subshell and 4s subshell very close in energy. So the first law of transitions element can use 3D and 4s subshells to form the C of delocalized electron. Therefore, higher electrical conductivity. Okay, so that's it from me today. Okay, so shall we back to the moderator?
Okay, with God's grace, we are done with today's section. We have learned a lot from Teacher Tang about physical properties of transition matter. Congratulations to those who are able to follow our section from the beginning till the end. And thank you very much, Teacher Tang, for such an interesting lesson. Okay, before I provide the certificate link, right, I will announce the last 2 passcodes, which are 3 and 4. 3 dan 4. Okay, now you can check the chat box for the certificate link. Please off the live chat button and click subscribe button if you haven't. This is to show your appreciation to Teacher Tang for giving you a free lesson. Don't forget to click the bell button so you won't miss out any new video and live classes from Teacher Tang. If you like today's class, then please click like and share it to your social media friends. Let's share the knowledge you received today with them. Sharing is caring, right? When you have finished, type done in the chat section, then I will give you the certificate link. Okay, once again, I would like to thank you, Teacher Tang, for the interesting lesson. Thank you also Teacher Vivila and Sir Shannon for being with us today. I think that's all for now. See you in another section. Please do remember, stay at home. Goodbye everyone. Have a nice weekend.
Wow, banyaknya hadiah menarik menanti anda. Wah, kini Akademi YouTuber mengambil inisiatif baru di mana memberikan hadiah-hadiah ini secara percuma. Ya, percuma kepada anda semua. Bagaimana caranya? Dengan mengikuti kelas tuition online percuma Akademi YouTuber sambil mengutip mata kredit, anda dapat menukarkannya dengan hadiah-hadiah yang menarik ini. Tunggu apa lagi? Segalanya percuma. Jangan lepaskan peluang tau. Dah dapat banyak hadiah menarik, takkan nak lepaskan peluang. Layari www.academyyoutuber.com sekarang untuk maklumat lanjut.
Dibawakan kepada anda oleh Akademi YouTuber.